similar to interfaces are so-called abstract classes. And those two are actually very often confused among programmers. So what we can also do is we can define this shape not as an interface, but as a so-called abstract class. So abstract class shape, and then we say we have an abstract val area, which is a float, and an abstract val for the circumference, which is also a float. If we then get rid of our shape interface and also call the constructor here of this shape abstract class, which does not have real constructor arguments, but every single class still has a constructor. And if it's empty, we just need to invoke it here via these opening closing parentheses, similar to a function without any arguments. If we do this down here, then everything else is the same. So if we run this again, then we will see we get the same area because we can still sum all kinds of shapes. And we now make this an abstract class. So what's the difference? An abstract class is in the end a real class blueprint again. So it's not only meant to define a contract like an interface does, to say, hey, the subclasses need to have this area and the circumference, because the moment we mark such a val or a function, by the way, as well, as abstract, that means, hey, we don't need to implement this here directly. But if a class says, I want to be a shape, then you need to implement this. And that again works via override. And abstract classes also have the behavior that we can't create instances of this abstract class directly. So we can't simply say that, hey, I just create a generic shape. I want to be a shape. This doesn't work because we can't create instances of abstract classes. We can only create instances of child classes of an abstract class. And this is what we call inheritance in object-oriented programming. So the moment we say a rectangle is actually a shape, then the rectangle inherits everything from the shape, or at least everything we define to be inheritable. In this case, it's really just the area and the circumference. But the main difference between an abstract class and an interface is that an abstract class can have normal functionality as well and also internal state. So wouldn't make any sense in this case, but just to show you the idea, we could have a counter variable here that starts at 0, and we then provide a function that actually increments this counter, and we say counter plus plus. That works because we've defined it that way. Every single subclass of shape will also get this behavior. It will also inherit that. So we could now go ahead and say rect1 dot increment. So even though we did not define this increment function directly in our rectangle, because it inherits from our shape class, which defines this behavior, not as abstract this time, because we have a concrete implementation here already. That means the rectangle and the circle will also have this function inherited from the parent shape. And they can also access this counter variable that comes from the parent. So if we now print this, print rectangle1 dot counter, then that will contain 1. So every single individual rectangle can now have its own counter value. If we have two rectangles, then the first rectangle has its own counter and the other rectangle has another counter. And they don't get in each other's way. So that is what I mean with internal state. In general, when you hear someone speak of state in the programming world, that just means to a value that can change over time. So in simple terms, just a var here. And this is something we can't do with interfaces. So that we have real values, like a counter that we can increment over time. We can provide default implementations of functions for an interface, but we cannot have variables in an interface that we already set in the interface directly and that we change directly in the interface. In most cases, you actually want to use an interface, but sometimes if you actually need a class to have such internal state and be inheritable, then an abstract class is what you should choose. You'll notice that if we remove the abstract keyword and also here, then we have to provide an implementation of these values, and then we also can't inherit from a class anymore. So normal classes or data classes are not inheritable. If we want a normal class to be inheritable without having this abstract behavior that we can't create an instance of this shape class itself, we would need to make the class an open class. So that is also a keyword that we can use here. And then we could say, okay, we actually have an open val area and an open val circumference, but we still get an error because we do need to provide a valid implementation here in the parent class already. Open just means, okay, we can inherit from that, but it also means it's not forbidden to create an instance of this shape itself. So it wouldn't make any sense in this case because we can't just have a shape. We always have to have a specific shape, a rectangle, a circle, some kind of polygon or so. But just that you have heard this once, that this open keyword exists, we would need to provide a default implementation here. Let's say 0f, for example, and 0f, then it wouldn't complain anymore. And we could still override this. So for all rectangles, this ruling is applied. For all circles, this one is applied. But nobody will actually complain if we don't override these fields. If we don't do that, then simply the implementation of the parent class will be used, which is, well, just returning 0 for all circumferences and areas. And with open classes, we could then also create a shape that is really just a shape. So invoke the shape constructor. And as I said, it wouldn't make sense because this would return 0 for every area, since there is no ruling behind how an area for a generic shape is just calculated. So here it really doesn't make sense to do that, but it's important that you've heard this open keyword at least once. But I want to quickly revert this to have an interface, because that is really the kind of correct approach in this specific scenario with these shapes. Since our shape parent class does not have an internal state, we should make this an interface, have a val area of type float and a val circumference like this. And then an interface does not have a constructor, so we need to remove these parentheses again. And here we need to implement this again for the circle. So Command I, hit enter, and we say, okay, the area is actually radius times radius multiplied by pi to float we had. I could have just undone all this, but it's also quick to rewrite this like that. And we have the same code as we had before. And of course, what I didn't show you, we can have functions in an interface as well. So we have some kind of, I don't know, I can't think of a useful function here, but a hello world function. If we say this takes in a counter, I don't know, then we would actually need to override and implement this hello world function in each of these classes that conform to this interface. That of course also works, but let's get rid of that. If we have such interfaces and specific child classes that implement this interface, then we can also check which specific type a specific shape is actually. And that actually works really nicely with a when expression. So we could say, when our circle is actually of type circle, then we say, yo, that's a circle. And if it is a rectangle, then we say, that's a rect. We do get an error here because it says incompatible types, rectangle and circle. Because here where we create the circle, the code already knows this can only be a circle, obviously. But if the circle would actually be created as a shape, and we would get this in a function, for example, here, this would make more sense that we have the when expression down here, where we don't yet know one specific shape of the shapes list is. So we could say we want to print all these shapes as well, maybe in a separate function, print shapes, var arc shapes like this. We then have our when expression here, when the current shape we're looping over. So for each shape in this shapes list, then for every single shape, we can now, if that shape is a circle, we print, yo, that's a circle, and otherwise that's a rectangle. So we can now say print shapes, rectangle 1 and circle 1, and if we run this, well, then it will say, yo, that's a rect for the first one, and yo, that's a circle for the second one. So that's also important to know that you can make these type checks here very, very easily with a when expression. That of course also works with if. So if you just need to check for a single type and not for all of them, then you can also say if shape is a circle, and then only do something here if the current shape you're iterating over is actually a circle. Something you will notice is if we actually don't print something here in the when branch, but rather return something like val output and then print the output, that's something we've done before, it actually complains because the when expression must be exhaustive. So we need to add an else branch here and actually also map these to the raw strings and not to print line statements. So if it's not a circle and it's not a rect, what kind of value should we then assign? So a when expression always must be exhaustive. So for all different possible scenarios, there must be one proper mapping if we want to just get a clear string out of that. For the print line statements here, it wasn't an issue because if something was not considered here, then the when expression simply wouldn't have executed any code at all, which is not an issue. But if we always want to print something and always want to get a clear string out of that, then we need to define a default behavior here. For example,